So when you watched the videos yesterday, you all learned that as long as Gauss's law is correct, Gauss's law, which it is, experimentally anyway, it seems, you learned that the electric field within any charged conductor is what? Zero. It's zero, no matter what. No matter what. If it's not zero, as we'll learn when we study electric potential, meaning voltage, if it's not zero, then charges will be accelerated by the electrical field and hence the electrical force until the electric field inside the conductor becomes zero. Okay, so we can see it experimentally, visually. Like Gauss's law is easy to see why that's the case, because when you put a Gaussian surface within a charged conductor, we know all the charge resides on the outside. The excess charge resides on the outside, on the surface. So if you draw a Gaussian sphere inside, or any Gaussian surface inside of the conductor, it's enclosing zero charge. If you're enclosing zero charge, you have zero electric field, right? According to Gauss's law. And this has profound implications when it comes to electronics. Because there's certain, especially when you deal with modern electronics, where you have very sophisticated, very sensitive pieces of electronic equipment. If you need to shield those electronics from strong electric fields, because those electric fields might damage them or cause them to operate incorrectly, then all you have to do is put them inside a conductor. Put them inside a little metal box. And that will actually shield the electric field from the object inside, because that object is now within a conductor that will have zero electric field inside of it. Okay, so there's interesting things for that. And then if you're ever in your car in a thunderstorm and you want to escape the lightning, don't get out of your car. Yes, if the lightning bolt is strong enough, it can actually go through the car and actually burn you, but you're not going to get electrocuted, because the car operates as what we call a Faraday cage. And that's what we're going to watch a short video about Faraday cages here, and then show another video that shows some dramatic applications of Faraday cages. But a Faraday cage is simply a metal enclosure that shields the object inside from any external electric fields. How does that happen? Well, the charges, like you saw in the video yesterday, Gianni, the charges in the conductor will just rearrange themselves in order to counteract the external electric field that's trying to permeate the Faraday cage, the conductor. Yeah. Like airplanes. Like airplanes. Yeah. Yeah. Chances are you're not going to get electrocuted if your plane gets struck by lightning. Yeah. Have you experienced that? Probably.
There was this one time.
There's this one time you're in a plane and got struck by lightning. Okay. So here's a short video. Let me zoom in on it so the folks at home can see. So this is actually an MIT demonstration from an MIT professor. You might have heard of MIT. It's a small college in Massachusetts. It's relatively unknown, but.
Does MIT stand for Massachusetts Institute of Technology?
It does. Hey,
wow. Well,
someone actually has heard of it.
Massachusetts is tiny.
Massachusetts.
No, it's a mass.
Okay. So here's a demonstration of a Faraday cage.
So today we are going to learn.
That's not what I want.
Oh, yeah.
So why doesn't the speaker do that? Like, is that a physics thing?
What is what?
Why does the speaker pop like that? Is that physics? Is that electric?
Yeah. Oh yeah. Interference. Electromagnetic.
10-yard penalty.
So today we're going to learn about electrostatic.
Just lousy kids.
Faraday cages and why it's not such a bad thing if you're in a lightning storm or something.
Subtitles.
And I don't want to do that with me, so we're going to do it with Benjamin. We have Benjamin Franklin wearing a nice.
Okay, let me start one more time. I'm sorry.
Skirt.
This is Gianni's fault for not watching the videos yesterday.
So today we are going to learn about electrostatic shielding and Faraday cages and why it's not such a bad thing if you're in a lightning storm as long as you're inside a car.
We will play with one of these things soon, Van de Graaff generator, when we study electric potential, aka voltage.
And I don't want to do that with me, so we're going to do it with Benjamin. We have Benjamin Franklin wearing a nice little Hawaiian hula skirt made of tinsel, and he is about to be in a thunderstorm. We are going to make our thunderstorm with a Van de Graaff generator. You can think of the belt and the Van de Graaff generator going around like this as analogous to the air circulation underneath the thunderhead as the thunderhead builds up. And then you can think of this up here as the analog of the cloud. So as soon as I unground this, it's going to start charging up. And you see Mr. Franklin there getting a little bit uncomfortable. You see his hula skirt streaming out behind him as he is in right now in quite a large electric field. And
Something to remember, if you're ever in the middle of a thunderstorm and you're outside and you start getting that static feeling, you're in trouble. And you need to get to low ground. If you can't get to low ground, you want to crouch as low as you can. You do not want to lay flat on the ground. You want to crouch as low as you can and make sure that your feet are still, if you're wearing shoes with rubber soles, you want to make sure your feet are still touching the ground. Okay? If you ever experience that sensation, that means there's a good chance that lightning is about to strike.
as you can get a sense there, he's not so happy at this point. Maybe I'll turn it up even higher. There you see, I've got a lightning bolt going to my grounding rod, and as you can look at what's happening to Benjamin as the lightning bolt hits the grounding rod. There we go. Benjamin is not happy. So now what we're going to do is we are going to have the same thunderstorm, the same electric field, but we are going to put Benjamin in a Faraday cage. So to put him in the cage, I'm going to start by turning this off, and we'll ground him. And here's my Faraday cage right here. I'm going to put Benjamin in the cage. Here we go. Okay. Benjamin's going to be in the same spot that he was before, same tinsel skirt that he had before, but this time he is in a cage. Like, for example, you're in a thunderstorm, but you are safely in a car. So let's see whether it is indeed safe.
So even though this Faraday cage is not solid, this guy, if he tries to create an electric field that points in, that electric field exerts forces on the free moving charges. So those charges will move until the net force on them is zero, which means if this guy's negatively charged, the excess electrons will move over to this side, right? If this guy's negatively charged, then actually let's say he's positively charged just to make it easier to conceptualize. This guy's positively charged, he has electric field lines that point in here. And then the electrons on this side are going to migrate towards that because they're attracted. They move in the opposite direction of the electric field until the net force on them is zero. Once the net force on them is zero, they've created an electric field. If there's an electric field pointing this way, the electrons that were here are now here. Now you have excess positive charge here that exerts a field this way, counteracting the field created by the external field source. Okay? And if the field within or on the surface of the conductor was not zero, or within the conductor, I should say, then the electrons would be accelerating, right? If they're not accelerating, if they're at rest within the conductor, at rest as far as classical physics says, if they're at rest, then the electric field has to be zero, right? So.
There we go. Let's turn on the thunder, or the lightning rather. Let's turn on the lightning. Now, if you look, you can see that there's lightning hitting the cage. There's that lightning bolt going from the Van de Graaff right to the cage here. And you can see that the cage has a very considerable electric field on it. If I look at the tinsel over here on the far side, which is streaming out behind it just like the tinsel on Benjamin was before. But now look inside at Benjamin in there, and I have to be careful not to touch the cage. But now look inside at Benjamin in there, and his tinsel is completely motionless. Benjamin is completely comfortable in there, calm, at rest, while the lightning storm rages around him, literally around him, and I just got me. If I touch that, I get shocked. Okay, that's what I just got shocked. But Benjamin is completely safe. This is the phenomenon of electrostatic shielding, and this kind of a cage is often called a Faraday cage. And we'll now turn the lightning off.
So that's Faraday cage. Let's look at so if you're, I think that's Mr. Lewin. Oh no, that's Mythos. So you can do very dramatic demonstrations with Faraday cages. if you're very confident in your engineering skills and your build skills, you can actually not just create a Faraday cage, you can create a Faraday suit. And then you can do crazy stuff like the Lords of Lightning. I would do this because I'm not this confident, and definitely not this confident in my engineering skills or build skills. But these guys are nuts, and they're really good, really talented, really smart. So they're literally going to be wearing Faraday cages.
I've seen those.
You sound on those? Oh. Not those suits. That electricity would kill it easily. Notice how the crowd has to be significant distance away. Get out of there. Anyway, so those are wearable Faraday cages.
Why doesn't it still burn them? I mean,
What's that?
Wouldn't it still get hot and burn them?
Not really, because the electricity just gets channeled right into the ground essentially. Maybe it probably gets warm.
How much current are they doing with the thing?
I have no idea. It looks like a lot. It looks like a lot of current. Yes. All right. Okay. So that's whenever you have a question saying what's the electric field within a conductor, just remember the Lords of Lightning. Because if the electric field was not zero within the conducting suit that they're wearing, then they'd be in a lot of trouble. A lot of trouble. Okay. So let's extend yesterday's lesson. I'm sure you're not dealing with it. I'm sure. What? Okay. So yesterday we talked about finding the field. Just for those of you that don't know because you didn't watch the videos. We had a charged insulating sphere. Let's say it has net positive charge uniformly distributed throughout its volume. Yesterday's video lets you determine the electric field at a point by drawing a Gaussian sphere inside. Okay. So let me turn this back around. Okay. Notice I didn't draw the three-dimensionality now because we're going to get to situations where if I try to draw them in 3 dimensions, just understand this is a sphere. This is a 3-dimensional Gaussian surface, a 3-dimensional or a 2-dimensional shell existing in 3-dimensional space. Okay. So that's an insulating sphere, and the relationship between distance from the center and the electric field is very different than the distance from the center and the electric field outside of the sphere. So watch yesterday's video, one of them, about that. Then we talked about a conducting sphere, which if you charge it, the charge gets distributed on the outside surface. If you deposit electrons on it, then the electrons move to the outer surface. If you remove electrons from it, then the electrons evenly distribute themselves within the conductor, leaving net positive charge on the surface. And then, so if you draw a Gaussian surface inside, there's zero charge enclosed. When I do my integral here, I get E times the area equals 0 over epsilon naught, 0 electric field. Gauss Law tells us that you get 0 electric field. Okay. For both of these scenarios, if you draw a Gaussian surface on the outside, the enclosed charge is simply the total charge, and it operates exactly like a point charge, right? There's no difference. If the field here could be this collection of charge here, or it could be all that charge concentrated into a point. I get the same field strength because I'm enclosing the same amount of charge at that distance. Same thing here. These guys are same radius, same charge. This guy's a conductor, that guy's an insulator. A distance from outside the radius of the actual sphere, a distance away from it, the same distance, you get the same field because you'd be enclosing the same amount of charge. Make sense? Okay. And then we use Gauss's law to determine the electric field due to an infinitely long insulating rod. An infinitely long insulating rod. which, again, we don't see many of those in reality, but we do see charged objects that are very long in relation to the distance away from them where we're interested in the field. If this was an electrical wire with current flowing through it, as long as the current density is constant, then it operates just like a charged wire because you'd have the same charge per unit length throughout. But we'll save that to our circuits unit. But in that case, you have this charged rod or wire with current flowing through it that creates an electric field. If the wire is 2 inches long, that we can consider that to be infinite if we're talking about the electric field a micrometer away from the wire. That's fine, right? That'll work just fine when it comes to engineering. But when we analyze this situation, we had to use a Gaussian cylinder. I'm not going to go over it again because you all saw it yesterday. We had to use a Gaussian cylinder where the point that we're interested in the field is on the edge of that Gaussian cylinder. No flux through either end. All the flux goes through the wraparoundy area. Right? And so we used Gauss Law to do that. Remember, this problem was the one where we had to integrate from negative L over 2 to L over 2, where the angle varied, where we set up that really nasty looking integral that we couldn't even do because we couldn't do it. We had to look it up in a table, right? So that was, and it took 2 pages. Like my notes for that problem take 2 pages. Doing it with a Gaussian cylinder is like 4 or 5 lines of math. It's real easy, real easy. Setting it up is important though. And that's where we stopped. So the last thing that we're going to use Gauss's law for, until we get to more complex situations, is using Gauss's law to determine the electric field due to an infinitely large sheet, or just a large sheet, right? Which we did already with the hoop, the thin ring, and then integrating all the electric fields due to all the thin rings that make up an area. Then we determined it that way. So using Gauss's law, as you'll see, makes it a little bit easier. So if I have a sheet of charge, and if this is a circular sheet or a square sheet, very symmetrical, and I put my Gaussian cylinder right in the middle, then it doesn't even need to be infinite because any electric field lines that come in from this way will be compensated by ones that come in from that way. It'll only be different if I start moving them towards the edge, right? And that's why when you become an engineer and you talk about capacitor plates and capacitors, you have what are called edge effects. When you start getting to the edge of the capacitor plates, the electric field behaves a little wonky, but there's ways of dealing with it. Yeah.
But if it's infinitely long, then it can't really get closer to the edge.
Right. That's why if it's infinitely long, it doesn't matter where you put the Gaussian cylinder. So I'm going to say to infinity. And beyond. To negative infinity. And negative beyond. Right. So here's my sheet of charge. Now, when I had a rod of charge, I put my Gaussian cylinder concentric around that. Okay. And again, you can use any Gaussian surface. Any closed Gaussian surface will allow you to determine the electric field at any point due to that object. However, if I used a Gaussian sphere here and had like half of it above and half below, the electric field, you can't be confident that it is constant over the entire surface. Okay. Definitely the dot product of the electric field and the area vector will not be constant. And so it would be a poor choice for a Gaussian surface. So I'm going to choose a Gaussian surface that will work here, and it's going to be a cylinder. And so on the top, it'll look like this. Take my Gaussian cylinder. This is the intersection between the Gaussian cylinder and the sheet. So above, it's going to look like this. Actually, I should dot this. And then below, it'll extend out this way. I tried to do that as best I could. You kind of making sense? This is a flat sheet with a cylinder that's going from the top to bottom. Okay, same distance above as below, although that probably won't really matter here in a second. Now, what you want to convince yourself of is that, and this coincides with the determining the electric field using Gauss's law for a infinitely long rod. Because of the symmetry, the electric field in the x direction, the electric flux in the x direction for this closed surface is 0. Because for any amount of charge on the sheet that's shooting some flux out this way, there's going to be some charge on that sheet that's shooting some flux out that way, where the x components will always cancel. Right? For an infinitely large sheet, there's no, even if it's inside, you got a dq in here creating flux going this way, you got dq out here creating flux going that way. The x direction flux is 0. Okay, there's no flux through the lateral surface area, right? So the only flux that we expect to see is the flux through the end caps. Let me draw this a little better. This is bothering me. The only flux through the cylinder is the net flux is going through the end caps. Okay. And so I got my diagram here. Because I know that and I could say by symmetry. I can spell symmetry. How do you spell symmetry? Is there 2 N's? M's? Okay. Symmetry, the electric field in the x direction is 0. As long as that's the positive x-axis and this is the positive y-axis. The electric field in the x direction is 0, which tells me the electric fields emanating from this portion from within the Gaussian surface, the only ones I'm interested in, because this is the charge that's enclosed, right? The charge that's on that circular piece of the sheet. So that electric field is going to point out this way. If it's positive, right? Yesterday I did do an example, as you all know. And actually I shouldn't say positive Q because this is infinitely large. So if this is infinitely large, how much charge is on it? An infinite amount. So I'll say positive area charge density, lowercase sigma. Yesterday I did do an example where we used negative charge, just to show how you deal with it if it's in the opposite direction. Not only do I have electric flux going up though, I have electric flux going down and pointing out of the bottom cap. Okay. So I have flux going out the top, out the end. Yes, I do have flux going this way, going that way, but it's compensated by flux, so it'll be going the opposite way. Okay, so the x direction flux is all 0. X direction field strength is all 0. Okay. Okay. And obviously there's no, yeah. And so now I can just use Gauss's law. And you'll see in this application, if you set this up right, the application of Gauss's law is super easy. Super easy. Barely an inconvenience. You guys don't know pitch meetings? Oh, gosh. Pitch meetings. YouTube. Watch it. You'll love it.
What is it?
It's a guy that plays every part in the videos, and it's like a movie producer, and the guy that makes the pitch for the movie. So he takes a movie and then pitches it to himself, to the producer.
Flipping physics.
But he's really funny. Just like flipping physics. So I'm going to apply Gauss's law. Notice that I've set up my surface so that the flux, the electric field strength is constant. Really, this should be dotted too because it's inside. And then it comes out right there. Right, it comes out of the end cap. Notice that as long as the x direction electric fields are all 0, then I have the same electric field at every point on the circular end cap. Right? Same as down here too. Right? And even though this is pointing down, it's still positive flux because it's going out of the surface. This is positive flux because it's going out of the surface. So, E dot dA, again, if you need to write this every time you use Gauss's law, that's fine. I mentally do this at least. E dot dA is just E dA cosine theta. Well, again, I don't need to worry about the lateral area here, but my dAs are all pointing straight up. Here, they're all pointing straight down here. They're all parallel to the electric fields. So E dA cosine theta, the cosine of the angle. Yes, I'm recording. Oh man, I forgot to zoom back out. I don't think I missed much. Sorry guys at home. And the cosine of the angle is 1. Right? This is why choosing a convenient Gaussian surface will make your life easier. So now it's just EDA. So the left side is just the integral of EDA. And that equals, well, the enclosed charge I can write in terms of charge density, right? Sigma itself is just charge per unit area. And it's pi r squared, right? Pi r squared. But our choice of Gaussian surface is arbitrary. The radius is arbitrary, the radius of our Gaussian cylinder. So I'm just going to leave it like this. It's just going to be Q over A. So that's the charge density here is total charge over total area, or the enclosed charge divided by the area that's enclosed by the Gaussian surface. In this case, just the area of this circle. So with that, I can write an expression for the enclosed charge. And that's just going to be charge density times the area. And that should make sense, right? The total charge on this circular segment of the area is just the charge density times the area. That tells you how much charge is there. So I can plug that in for Q enclosed. I get sigma times the area over epsilon naught. Electric field is constant, and that's why I said I want to make sure the Gaussian cylinder is the same distance below as it is above, because then the electric field here at the surface of this surface is the same as the electric field there. So the electric field is constant. I can bring it out times the integral over the closed Gaussian surface, the entire Gaussian surface, but remember the flux through the sides doesn't matter. That's going to equal sigma A over epsilon naught. Now here's where we need to be careful. I have flux going through two surfaces, right? Notice that the area of this surface is the same as the area of that surface, right? For a cylinder, same as the area of that surface. So when I add all the areas that have flux going through them, it's going to be this guy plus that guy. I got two of them. Two of them, two areas. So doing this closed surface integral, which again seems complicated, just means add the area of two circles. That's it. Wait, what? Someone say wait?
Just saying wait.
Oh, I thought you said wait. That equals sigma times area over epsilon naught. Everybody brought A to the party. Hey. That cancels. So what's the electric field due to an infinitely long sheet of charge? Sigma over 2 epsilon naught. Remember this when we derived that? I said remember this because you're going to need it for when we do capacitors. Now, to do that before, we had to take the flux due to a thin ring and do a nasty problem to figure, not nasty, but involved problem to figure out the electric field due to that thin ring a distance away. And then we could add up the electric fields due to an infinite number of infinitesimally thin rings that make up an entire area and add up all those electric fields. And then we take the limit as that area approaches infinity in extent, and the electric field is sigma over 2 epsilon naught. And it does not depend on your distance from the surface. Right? If this table was infinite in extent and had uniform charge density on it, the electric field right here would be the same as the electric field a billion light years that way. Okay. In practical reality, all that means is that a charged plate this big, the electric field 1 micrometer above the surface will be the same as the electric field 1,000 micrometers above the surface. Okay, so as long as the distances are small in relation to the lateral extent, the electric field is constant. And this is why capacitors work so well, because you charge a capacitor, it has a positive plate and a negative plate. It creates an electric field in between the two plates, and that field is constant within the entire space, except for, again, at the edges. But edge effects are beyond the scope of this class.
Is it constant or constant?
It's constant for small distances compared to the lateral extent. Like you would measure with sensitive tools, you'd measure the same electric field. For small distances in comparison to the areal extent. Yeah. Cool beans? All right. So let's talk about one other thing, and then we'll spend the rest of today, it won't be long, and then tomorrow, and then Friday on the Gauss Law Quest assignment. I changed the due date to Friday night. It's not due tomorrow. Except for Connor. Still due tomorrow night for him.
Just like the video that was yesterday.
What's that? Yes.
I'm gonna watch it tonight. The only reason I didn't was I didn't realize how many things my other teachers actually had me doing.
You didn't watch them?
I would have watched them at 10:48.
It's too bad I gave a grade for that.
Well, look, it's 10:48, almost done.
Oh, okay.
Oh, yeah, there's something that's not very I don't know.
Okay, so now notice that what we just did was a thin sheet of charge. And by thin sheet of charge, that's weird. A thin sheet of charge is not exactly real. So let's talk about a conducting, like a conducting sheet, a thick conducting sheet. And now I'm not going to draw it three-dimensionally because we got to look at the dimensions of the sheet itself. So let's say we have a conducting sheet that looks like this, conducting. So this will be a thick conducting sheet. What's the electric field here? Wait, let me charge it first. Let's charge it. We'll give it positive charge.
Where's your cord?
Give it positive charge. That positive charge will distribute itself over the surface. It will concentrate in the corners, but I'm just going to kind of draw it evenly distributed for now.
Does it have edges?
What's that?
Does it have edges?
Yes, but we're not going to worry about the edges because it's going to be really long. Let's say, yes, it is. For practical purposes, infinitely long. However, it does have some dimensions in the thickness. Okay. So, here's the deal. Let's say I want to know, what's the field here? Zero. What's the field here? Here.
Positive.
Zero.
Still zero. Yeah, it's zero. Electric field within the conductor is zero. So there's two ways that I can determine the electric field on the outside here. But the thing, and you can kind of think of it this way. I now have charge on the upper part and the bottom part, right? So if I did it the same method as last time, then I would expect to have twice the flux, right? If I had the same charge density here and here, and the distance from those plates doesn't factor into the actual total amount of electric field because this is infinitely long, then wouldn't I have twice the flux that I would have if it was just a thin sheet with just one layer of charge on it? That makes sense, right? Hopefully. And if it doesn't, we can draw a Gaussian surface like this. It will be a Gaussian cylinder, but we're looking at it from the side, so it will look like a rectangle. I'm going to put my Gaussian cylinder like this. Right. There's my Gaussian cylinder. No flux here on this side. None. All the flux is coming out the top. The electric field lines go out the top. The flux is going out the top. No flux here because there's no electric field there. No electric field inside the conductor. And it is a cylinder though, so that top end cap is the area of a circle, which is the same as the area of the intersection. This doesn't need to be a cylinder. It could be any prism, right? But cylinder, because we use cylinders for long conducting wires or rods, use a cylinder here and it's fine. The age just cancel out, so the area actually doesn't matter, as long as the intersecting area is the same as the area through which the flux is flowing. So using Gauss's law, integral of E dot dA. Hopefully this is a lot less scary now, right? The closed surface integral of E dot dA sounds complicated at first, but then when you see how to use it, it's actually really easy. Get out of my house. Okay, and so if this guy is infinite in extent, we will call the enclosed charge, well, we'll define the enclosed charge in terms of charge density. Again, this could be the area of a circle if we're using a cylinder. It could be the area of a square if we're using a square prism. It could be the area of a star if we're using a star-shaped prism. Doesn't matter, because it will always cancel out. And the integral then, same thing happens here. I have the electric field, it's constant on the surface. dA, now I only have flux going through one circular area, not two, just one, because the other end, there's no flux to it, because the field's zero. So this integral is just A, right? The integral of E dot dA is literally EA. That's it. It's in the gate. And that equals the enclosed charge is the... Sorry, I forgot to rewrite it. I can write the enclosed charge as sigma times the area. So I just put sigma times the area over epsilon naught. Areas cancel, and I get the electric field is sigma over epsilon naught. Which is twice as much as it would be if it was just a single sheet of charge density, right? Note that if I were to extend this Gaussian cylinder all the way down, remember, this hinges on the fact that you realize there's twice as much charge in this cylinder if it's the same as the last situation. Because in the last situation, you have a thin sheet. And by thin, we mean so thin, there's only one layer of charge on it. Now, if I have the same charge density on this side and this side, I have double the charge. I have double the field. Sigma over epsilon naught is double sigma over 2 epsilon naught.
So that also means when it comes to if an infinitely expanding thick sheet, the thickness of the sheet doesn't matter.
Right, exactly. Yep. Which again, in reality, and I always point this out because it's like, we only deal with infinities in math, right? In theoretical mathematics. And yeah, that's theoretically true. Like explicitly that's true. But in science, in physics and engineering, very often the comparison between the area of one thing and the distance of another thing is so great that you can just say it's infinite. And your error can be literally immeasurable, right? So it's okay to be dealing with infinities in these cases. Again, when we get to our unit on capacitors, I'll take one of these little capacitors and I'll slice off the top and I'll pull the innards out and I'll unroll it. And it's just two metal slits. It looks like foil separated by a really thin piece of paper. And the distance between the two slips of foil when they're next to each other is so small in comparison to the area that's formed by this. I mean, it's long, so it's a long area, but it's really like short. The width is very small. The distance between the two plates is so small that you can consider the area of something that's like this wide and this long to be infinite, right? And it works just fine. It works just fine. This is from a disposable camera. Do you guys know what disposable cameras are?
The cameras that are disposable.
Yeah, but they use this stuff called film. Have you heard of film?
Yeah, it's like
Oh, you know photography. You know film. You ever used film?
No, I want to though. I just need to get film. It's just expensive.
It's such a pain, man. I feel like digital is. I remember when digital wasn't as good, but unless you're like a purist, I feel like it's not even necessary anymore. Because God, what you would spend a week in the darkroom doing, you can now do on a computer screen in like a half hour. So.
There's like people who claim that like vinyl is objectively better than digital, and it's just mathematically false.
Right.
You know,
Right.
Like Nyquist's law or whatever. It's like you like. I forget exactly what it is. If you can.
Now that used to be true.
I mean,
Well, as technology gets better, the waves get smoother.
so mathematically, if you have like 44.1 kilohertz sample rate, and all your sounds are below 20 kilohertz, and which is audible spectrum, all your signals can be represented because if you have a more precise signal than that.
Now I would say I understand what you're saying. That would hinge on the recording process being the exact same, right? The recording techniques, the recording materials, like getting the same audio data, the same exact audio data, just stored in two different ways. But recording analog and recording digitally, there are different techniques, and so it's not like I don't have I don't listen to vinyl.
Sure.
But
the video I was watching, like what you're saying is like, if it were true, like the claims that vinyl can store more precise data. What would happen is you'd have to have a speaker that can accelerate, like, I mean, these things have mass, obviously. You can accelerate in, like, instantly. But
Right.
Infinite.
Yeah. Yeah, there are purists out there, and yes, they are kind of annoying, but yeah, anyway. So take-home point for Gauss's law. Actually, before I get to that, well, yeah, let me write this. Gauss's law allows us to, as we've already seen, for a point charge or outside an insulating or conducting sphere, Gauss's law tells us something that we already knew. The electric field is 1 over 4 pi epsilon naught, otherwise known as K, but because using Gauss's law actually incorporates 4 pi epsilon naught, right, in order to get it written that way, times the charge Q over R squared times the unit vector R hat, or just KQ over R squared. The magnitude of the electric field, KQ over R squared. Gauss's law tells us that. It tells us for a line / rod / what else did I write? You could have an infinitely long cylinder is essentially an infinitely long rod, right? So cylinder. This is what we saw yesterday. We actually did this using brute force integration methods that are much less convenient than Gauss's law. But we did determine that the electric field due to this distribution is sigma over 2 pi epsilon naught times R. Again, times R hat. That just tells you the direction. If the charge is negative, it's negative. So if R hat points in one direction, then the actual field points in the opposite direction. Generally, we're just more interested in the field strength, and then you can just use your diagrams to say what direction it points. And so you can forget about the vector symbols in R hat and just say KQ over R squared. And then for a sheet of charge, as we just showed, and this, arguably the most important, although this is very important, but this is kind of easy, and it's on the formula sheet, or at least indirectly it's on the formula sheet. But for a sheet of charge, the electric field is charge density divided by 2 epsilon naught, and again, times the unit vector to put it in the right direction. So those are the biggies. Those are the biggie electric fields that Gauss's law can let us determine. That doesn't mean that every problem concerning Gauss's law is going to be those three things, right? There's going to be some questions on the current quest assignment to deal with. Slightly different stuff. You got to use your noggin a little bit. If you're going to see a Gauss's law FRQ on the AP exam, chances are, or there's a very high chance, it'll be like an insulating sphere. Surrounded by a conducting shell. Ooh. So I have an insulating, and let's say this guy is positively charged. So let's call that guy positive Q. And then we have a conducting shell.
Like a turtle shell.
Yes, like a turtle shell.
Said turtle shells aren't conducting.
How do you know?
I mean,
You ever trained them? How do you conduct electricity through a turtle shell?
Let's say they're both positively charged. Okay. And let's say the question says, and this is a very common, I've seen this on several AP Physics E exams. Very often you have to go from the electric field stuff to the voltage stuff, the electric potential stuff. But you might say part A, determine an expression for the electric field within the insulating sphere in the space between the insulating sphere and the conducting shell, within the conducting shell, and then outside of the conducting shell. Right? It's actually not as hard as it might seem. Because we all watched the video yesterday, we know that we can determine the electric field strength using a Gaussian surface within the insulating sphere. By the way, this distance is r, right, little r? For that little r, as you all remember, because you watched the video yesterday, if I want to plot the electric field strength versus r, is linear. It's a linear relationship between the electric field and the distance from the center within an insulating sphere. Right? If you watched videos yesterday, you knew that. Then once I get outside of that, kq over r squared. Right? If I enclose the insulating sphere, right, this is my new r. Say this is like r1, this is r2. Then that's just the electric field for a point charge. It's kq over r squared. You might say, what about this guy? What about this guy outside?
Oh, or 3.
But if we're interested in the field here, this guy's not enclosed in that Gaussian surface. Therefore, it doesn't create any electric flux through it. And you might say, oh my gosh. Yeah, that's it. Have a good day. We'll continue tomorrow.